History of Vector Analysis, Episode 19, Algebra of Vectors, Part 1. You are here. Hey, it's old Doc Oler. Welcome back. In the previous couple of episodes, I showed how Josiah Willard Gibbs and Oliver Heaviside independently modified quaternion algebra into what we today call vector algebra. They did this by changing the defined rules for addition, multiplication, and differentiation. Okay? This removed most of the elegance, and we might add coherence, of quaternion algebra, but it did serve the purpose of making Maxwell's electricity and magnetism a bit more user-friendly. Okay. If you are a physics major, troubled or not, then you have probably been doing vector math since high school. But until now, at least I suspect, vectors were presented without their extended backstory. Now that you have that backstory, I want to go over all that vector arithmetic again. It is my hope that you will now see these elementary fundamentals, okay, in a new light. All that stuff I said in the first episode about background, context, and perspective. Let's see if it works. I'm going to begin at the beginning with vector addition and subtraction. Hey, these are the fundamental properties, so I have to say something about them. The results are pretty normal, but it does lay the groundwork for the weirder stuff ahead. Okay, consider three arbitrary vectors defined thusly. Note again that I'm not using colors for ijk anymore to indicate that the ijk's are real and not complex. First up, does the commutative property hold for vectors under addition? Yes, indeed it does. You add the vectors term by term, and you can use the commutative property of addition for real numbers to show that v1 plus v2 equals v2 plus v1. Geometrically, this is the famous parallelogram addition rule. Okay, what about the associative property? Also yes, due to the commutative property of addition for real numbers. Okay, moving on. Next, in the set of vectors, is there an I whose properties are such that I plus any arbitrary vector v equals v? Why, yes there is. It is just this, 0i plus 0j plus 0k. All right, if we are going to at least try to treat vectors as normal mathematical objects, then we note that I has to be a vector and not a scalar because you can only add mathematical objects of the same type. Okay, just saying. So, the identity property of addition holds for vectors. Now the all-important inverse property. For every vector v in the set of vectors, is there another vector, let's call it inverse v, such that v plus inverse v equals I, the identity vector? The answer is indeed yes. It is -1 times v or minus v. This last property means that vector subtraction is defined as well as vector addition. V minus v equals 0. Before we get to vector multiplication, let's quickly take a look at the rules for combining vectors and scalars. Consider two vectors v1 and v2 and two scalars c1 and c2. Addition first. Is c plus v equal to v plus c? In referee mode, we have to put our foot down here and say no. Vectors and scalars are different kinds of mathematical objects, and it is a general rule that you cannot add different kinds of mathematical objects. We state that c plus v is not defined. Now in the past, mathematicians said that the square root of -1 was not defined, and you saw how that turned out. Okay, so let's not kid ourselves into thinking that this statement is some sort of absolute truth. It's a rule that, at least for now, holds in vector algebra and a lot of other places, but who knows what some crazy math nut will propose sometime in the future. What about the multiplication of a scalar and a vector? This, we can state with utter confidence, is defined in vector analysis. The rules are simply governed by the distributive property for real numbers. You can also see, I hope, that the multiplication of scalars and vectors is commutative. Yay! Okay. More generally, the distributive property holds for pretty much all combinations of scalars and vectors. Now, the fact that these rules of vector arithmetic actually hold might seem like much ado about nothing, but it's not. It turns out that the rules of vector addition and subtraction combined with the rules of multiplication of vectors with scalars is basically all the vector algebra you need to create the important and powerful mathematical field known as linear algebra. Linear algebra is essentially the mathematical language of quantum mechanics, and it is used extensively in computer graphics and in many other places as well. I will add in passing that it's a good thing that these are the only properties of vector algebra that linear algebra requires, because, as we will now see, these are about all of the conventional properties that vector algebra has to offer. Vector multiplication. Let's start out simple. What is the definition of the product of v1 times v2? Once we have this, we can determine whether vector multiplication is commutative and or associative. Okay, here are v1 and v2. Let's multiply them together in the standard way. We get 9 terms, and here they are. Now all we have to do is to plug in the values that we've decided on for the I squared, j squared, k squared, as well as the ij and ji products. Okay. If, by some chance, you just had a warning light go off in your head regarding the problems Hamilton ran into with triplets, then good for you. Okay, seriously. Uh-oh. It is perhaps at this point that we remember that what Gibbs and Heaviside did was define the dot product of I squared as 1, but they also defined the cross product of I squared as 0. What do we do here? The fact is, here comes a flash of perspective, I hope. The fact is that, at least in this old Doc Goller series, we have not defined the multiplicative product of v1 and v2. Gibbs and Heaviside defined the scalar product and the vector product of v1 and v2, but not the plain old multiplicative product. This has been a problem all along, actually, even when you were first exposed to vectors back in high school. The sleight of hand that textbooks and most teachers use to get around this type of thing is to use words to the effect of, okay, there are 2 types of vector multiplication, the dot product and the cross product. Okay, nothing up my sleeve. But if you want to get down into the details, you can see that this is not technically an accurate statement. Multiplication in algebra may vary from mathematical object to object, but there are certain things that they all hold in common, and this definition right here is one of them. Okay? The dot product eliminates the cross terms, and the cross product eliminates the diagonal terms, but neither set of rules is valid for the entire multiplicative product, if for no other reason than the 2 sets of rules are inconsistent with each other. So, what do? We need to answer the question, what is v1 times v2 in the general case? I mean, we have to answer this question, right? Don't we? Well, it appears that we do not. Okay? If you find the official answer anywhere out there, let me know. Okay? For what it's worth, sidestepping this requirement to answer this question is how we, at least, get out of having to deal with the real equivalent of Hamilton's triplet problem. You know, the one he never resolved. All right, so what we're going to do instead, ready, is to investigate the commutative, associative, and inverse properties of just the dot product and the cross product. Poof. First up, the dot product. Is the dot product commutative? Let's crunch it out. The good news is that we can see that v1.v2 is equal to v2.v1. The bad news is that both products are seen to be scalars. Okay, this is not surprising. This is why all those guys we discussed referred to the dot product as the scalar product. Still, there is this issue that the dot product of 2 vectors is not in the set of vectors. Okay, how can an operation even be defined if this is the case? Well, this might have been considered a fatal flaw prior to the 19th century, but now we have seemingly lost our faith in the absolute truth of such mathematical rules. We can, and we do, say that v1.v2 is commutative with v2.v1 because they yield the same mathematical quantity, even though that quantity is not a vector. So the answer is yes. Do you see how weird this is getting? What about the associative property of vectors under the dot product? Is v1 dotted into the quantity v2.v3 equal to the quantity v1.v2 dotted into v3? Well, we may note that the parenthetical expressions are scalars, and the dot product is only defined for a vector dotted into another vector. So v1.v2.v3 is not defined, whatever order you do the math in. So the quick answer is no, the dot product is not associative because the operation is not defined. This might ring a bit hollow, though, after what we just did with the commutative property. All right, let's suppose we define v1 dot, the quantity of two other vectors, as v1 times the scalar. That's defined, right? And we seem to be able to change our mathematical definitions almost at will now, right? All right, let's go ahead and check this out. We know that the product of a scalar and a vector is another vector with a different magnitude but pointing in the same direction as the original vector. Thus, via this geometric argument, we see that the product on the left is a vector parallel to v1, while the product on the right is a vector parallel to v3. That is, even if we get clever like this, v1 is not parallel to v3, and so we can state with some degree of certainty that the vector dot product is not associative. Okay. Also note that this last line allows us to avoid the question as to whether v1 dot v2 dot v3 can be considered defined. Whew! Do vectors have an identity property under the dot product? For this to be true, our standard definition is that there would have to be a vector I in the set of vectors such that v dot I is always v. So again, the quick answer is no. There is no vector in the set of vectors that returns anything other than a scalar when it is dotted into a vector v. But what if we change the definition of I such that I doesn't have to be in the set of vectors? Is there a mathematical object I such that v dot I is always equal to v? Well, the scalar 1 fits this property. Okay, what do we just say about the legitimacy or existence of a vector dotted into a scalar? Oh, right, we kind of avoided that. So now what? Can we claim that vectors have an identity under the dot product? Look, squirrel! Okay, generally, as far as I can tell, the community typically just finds a way to rewrite actual problems in such a way that this doesn't come up. Is an inverse property for the dot product defined? That is, for every vector in the set of vectors, is there also a v inverse such that v dot v inverse equals the dot product identity I? Well, if the requirement is that the identity object be in the set of vectors, then no, okay, because the dot product of two vectors is always a scalar. All right, what if we allow v dot v inverse to be equal to the scalar number 1? Well, then the answer looks like it could be yes. Okay, if you define v inverse as the vector v over the reciprocal of v dot v, the math works out. V dot v is a scalar, and we are allowed to divide a vector by a scalar. So yes, or maybe. Well, let's consider how we typically use the inverse property. The first application is almost always that we use it to prove that the property of division exists. So let's explore this. If we define the scalar a as the dot product of the vectors b and c, can we then define the vector b as scalar a divided by dot c? All right, ignoring the issue of the dot for the moment, are we allowed to have a vector in the denominator? Okay. The quick answer to this question, as explained in the very few textbooks where it appears at all, is no, you cannot divide anything by a vector. There's nothing to see here, folks. Move along. Okay, no inverse property for the dot product. Perhaps you are getting a better appreciation for why quaternists such as Tate were so appalled by vectors. We are about halfway through our discussion of the algebraic properties of vectors, so this is a good place to break. Unlike the previous episodes, I don't think that you lose much by coming back to part 2 of this one at some later time. On the other hand, perhaps you just can't stop with this. You gotta know how it turns out. All right, so until next time, whenever that turns out to be, see you then.